All right, well, you already heard my name. You heard where I work. I contribute to open source. You can find me on social media. Nice to meet you all. If you have heard my name, you've probably heard it in relationship to SQLite. I have been working a lot in the last 2 years to make Ruby on Rails the best web application framework in the world for building on top of the SQLite database engine. And I had the opportunity this September to talk about that and all of the work that is in Rails 8 at Rails World. Those talks are now on YouTube with subtitles in various languages. If you haven't checked it out, I would recommend it. I heard it's a really good talk. But today, I'm not going to talk about SQLite. I'm going to talk about one of my older passions, which is how to make background jobs reliable and resilient. This is a sequel talk of sorts to a talk I gave at RubyConf 2021 in Denver. That talk was focused more on a sort of introduction to the problem space. Like, what does it mean to make a job reliable and resilient? What are some of the core problems? This talk, I want to focus much more on the solution space. What does it take to build and test reliable and resilient jobs? And to guide that exploration, we are going to be looking at 2 gems that I maintain, which encode the core principles that I believe are essential to reliability. The first is a gem called chaotic job. This is a testing helper. This is going to help you test that your jobs are indeed reliable and resilient. And the second is a gem called acidic job. This is a workflow execution engine. This is what you can use inside of your jobs to help them become reliable and resilient. And we're going to use these as sort of guideposts to walk our way through the core principles and problem areas and how to solve them. So let's jump into it. And let's talk about testing. Because we really can't begin this discussion if we don't start from an understanding that it's kind of fundamentally difficult to know, is my job reliable? Is it resilient? Like, one way you can find out is run 1 million of them in production and see if it's problematic, but that's not like maybe the smartest or safest thing to do with your business, especially for business critical jobs. And the first thing that we have to tackle, that I ended up tackling, is like, how do you even test a job for resilience when you need to retry it? You need to have multiple executions of it. When I was reading through the Rails guides, I was like, oh, I see how to do this. This is straightforward. I'll use the perform in queued jobs block. I'll put my job in there. Transient error occurs. A retry will get scheduled. It'll get run again. It'll be fine. And those 2 executions end up, and I can then do my assertions. Straightforward. Yeah, unfortunately, that's not how it works at all. This is not a useful helper for testing production behavior. It should really be called perform instead of enqueuing jobs. The way it behaves is it actually effectively overwrites the enqueue method and just immediately performs that job when it was told to enqueue it. And what that means is, instead of enqueuing it, finishing the job, and then starting this new job, inside of the execution of this first job instance, it starts running the second job instance, which is not how production is going to behave at all. And of course, for good tests, we want tests that mimic as much as possible actual production behavior. Right? So performing queued jobs, don't use that method to test reliability. What can we use instead from the active job test helpers? Well, this is going to work much better, right? So we're going to work in a loop and say, if we have enqueued jobs, flush them. That means perform them. And so each time we run through the loop, the first time we have one job, we perform it, there's a transient error, a retry gets enqueued jobs has an element, so we come into the loop again, and we flush it one more time, everything goes fine, in-queue jobs is now empty, and we move on to our assertions. This is going to work like production. This is good. And I thought everything was fine, I didn't need to do anything more, until I started testing jobs that in-queued and scheduled other jobs. And I immediately found, okay, this is not quite what I need. Because the way that flushing queued jobs works, I learned, is that it's going to execute those jobs, perform those jobs, in the order in which they were put into that in-queued jobs array, which is to say the order in which they were in-queued, not the order in which they are scheduled. All right, so you have a job, it has it's going to schedule one job in the future, and it also has an error that we've forced in our tests. It schedules the job. Let's say it schedules it 5 minutes from now, some other job. And then there's an error, so the retry gets put in. So we have two elements in in-queued jobs. The first one is scheduled to happen in the future in our retry. This method is going to perform the thing that's supposed to happen in the future, and then after that, our retry. Of course, in production, the order would be flipped. We would retry that job in 3 seconds, not 5 minutes, so it would occur first, and then the next one. And if they happen to be talking to some of the same resources, those well, they're not really races, but the order of operations is going to be different. It's not going to mimic production. So what I came to see pretty quickly is that the active job test helpers are not really well built to test reliability. They are there to help you test performing a job once. What do we need? I came to think about it and believe that there's really only 3 helpers that we need, so I built them. The first thing we need is we just need a perform all jobs helper, right? That's going to perform jobs immediately, but in the order that they would be performed in production. So we're going to virtualize time and shrink it, but we're going to guarantee that the order matches production. We're going to execute jobs in waves. We're going to execute jobs based on when they're scheduled. But if we're dealing with scheduled jobs, when we're virtualizing time, we're going to need a little bit of control. So in addition to perform all jobs, you have perform all jobs before and after. And this allows you to ensure that you, for example, in that first case, perform all of the jobs and its retries and perform no scheduled jobs. So you could do a block of assertions to say, okay, this job ran and it had some errors and it had some retries, but it eventually succeeded. What's the state of my system now? Okay, those assertions are done. Now let me run the jobs in the future. Wait till that's done. Maybe they have some transient errors that I've forced. That resolves, and now I have a second block of assertions, right? So I can have manual control and make sure that I'm testing my system with the level of granularity that I need to be very confident that things are going to be working. And it's going to do a little bit, just a little bit of magic to sort of soften those time boundaries so that you actually perform jobs, right? Like if I say this is scheduled in 3 seconds, and I do that inside of the job, and then I say perform all jobs before 3 seconds. Those 2 time nows, right, they're going to have different seconds. They're going to have different milliseconds for sure. We want to make sure that it actually gets in there. So it rounds down by like 1 order of magnitude to make sure that it pulls those jobs. A little tiny bit of magic just to make sure that you're not losing any jobs in your tests. Those 3 helpers are what you need. This is like the foundational blocks for testing jobs. But once we have the ability to run our tests with virtualized time but the correct production behavior, how do we actually force failure scenarios? Right? Like this is really what we need to test resilience. We need to have errors. We need to have a very particular kind of error. If you imagine a simple job like this, I happen to know, because I wrote this code, that the weakest point in this job is right here. So I want to make sure that it behaves correctly if an error occurs between these 2 steps. How do I force that to happen? And how do I get very particular behavior, right? Because what I need here is a transient error, not a permanent error. There's no point in testing permanent errors. We know what's going to happen. Your job will try, end up in the dead set. The error is non-resolvable, so who cares? What we need to test are transient errors, something that went wrong once. When you retry it, magically it's fine, right? Rate limiting, flaky networks, there's all kinds of transient errors. So how can we force a failure scenario to test? Well, in this case, we can monkey patch this method to say, all right, I know in this test I want this method to fail. I need it to be a transient failure, so I need it to fail once. So I'm going to set up a little bit of state in my class to say, have I errored or not? Change the state, do the error, so the second time through it doesn't error and it behaves transient. And this will work, but this sucks. This does not scale. You don't want to have to write all of this code for every scenario, for every job that you need to test. We need a way to do conceptual compression, to borrow a phrase. So that's the other helper that chaotic job provides. It allows you to define a scenario. And a scenario allows you to inject a glitch into the execution of a job. And a glitch is just a tuple that says the position before or after and a particular line of code. And a particular line of code is just a file and a line. The actual engine will do effectively, it's implemented differently, but effectively what we saw on that last slide. And it'll run it, it'll use those perform job helpers to run the jobs correctly, run all of the retries, get to a final completed state, and then you have your assertions. What's the state of the system? This ability to have glitches, to inject glitches into code execution is really the heart of chaotic job. And what I found after I found this and built it was that this unlocked a really cool possibility. This unlocked the potential to run simulations. So the final helper method that you get is a run simulation. You just give it your job instance, and then you define a block. And inside that block, you can define whatever assertions you want. And what that's going to do, if we go back to our made-up job here, is that it is going to build up for itself a scenario for every possible error location in your job. What it does is it performs your job once, tracks all of the line executions using a trace point, and then says, okay, an error could occur here, or here, or here, or here. I'm going to take your block of assertions, I'm going to define those scenarios, run them to completion, run your assertions. And if you get that test to pass, now you have some pretty strong foundations to say, like, yeah, I think this job is resilient. I have tortured it in a high-level set of ways, right? Like, we're not going into every method that's called inside of like the backtrace of one method, but we're injecting these glitches into every possible line execution point in your code flow, and then you define your assertions. These are the state of the side effects, and if that passes, that's a really strong test. So altogether, these 5 helpers, I think, are an incredibly high leverage set of tools to get you clarity on business critical jobs. Are they reliable? Are they resilient? And that's not even all that chaotic job offers. That's like 80% of it. But this is the foundation upon which you can start to scale out reliability. But of course, right, how do you actually build reliable jobs? So you can find out, yeah, my jobs aren't very reliable. Chaotic job will help you with that. It'll show you precisely where you have problems. How do you solve those problems? That's where we turn to acidic job. A little bit of context. I think that it's definitionally true that every single business that has any background jobs has at least one business critical background job that must be reliable and resilient, which is to say it must be acidic. It needs to have atomic operations. The data state needs to be consistent in where it ends up. Right? The operations have to be isolated, and of course those side effects have to be durable. And in working in this space for many years, I have come to the belief that the best mental model to help you get to that place are durable execution workflows. So what in the world is durable execution workflow? Durable execution is a bit of jargon that comes from the microservices world primarily, that has grown in popularity in the last few years, that describes an approach to executing code that is specifically oriented around fault tolerance. Right, to say, how can we ensure that this code executes inside of some eventually consistent environment in a way that is correct and in order to do that, we need some durability. A workflow is a very simple concept. It's just a linear sequence of steps. Each step is some executable function, and you define that workflow in a way that can be serialized and passed to an independent execution engine. This is at the heart of many of these tools. And all of this is driving towards getting to idempotency. This is a fancy word that you are going to see anytime you are working in this problem space. It is fancy Latin for safe to retry. And what it really means is that your side effects only take effect once, regardless of how many times you run that job. And this is what you have to have. This is the essential characteristic of a resilient background job, because when you're in an eventually consistent environment where your code is going to attempt to self-heal by retrying, in order for your system to be correct, you have to know that running that code again from the beginning, because it's not magic, it's just going to start over from the very beginning, that you're going to not duplicate side effects. You don't want to send 40 emails to your biggest customer because your API rate limit was triggered, right? All of these things together help us get a little bit of a clearer sense of like, what do we even mean by a job? Right? Like a job is just an operation that runs in an eventually consistent environment, right? An environment that's going to try to self-heal through retries and is defined by the side effects that it produces, not the computation that it returns at the end, or the value that it returns at the end that has been computed. And this space of durable execution engines that you can pass your definitions to is growing quite large. Many of these companies here in this list are valued at more than $10 million. And one of the things that I love about the Ruby ecosystem and the Rails ecosystem is that we can compete with them for free on the weekends. And that's what a acidic job is. This is my attempt to take down these $10 million behemoths with a gem that has about 1,000 lines of code all totaled in it. So what is it? It's just a module that you include into any regular job. That module is going to give you a few methods. Let's walk through them. Primarily, it gives you this execute workflow method. This is the heart. This is where you pass over control to the execution engine. You're going to put this inside of your perform method, and you're going to allow the workflow engine to take control. It's straightforward. It takes two arguments. This block, which receives this builder object that you can only call the step method on, and you just define your linear sequence of steps. These symbols just map to method names. Those methods just have to be available on this job instance. By convention, those are probably going to be private methods defined inside of that class, but they can come through inheritance or composition or whatever. Just need to be available. And then you have this unique by keyword argument. This is a really important point, so I want to go into it a little bit. Like, uniqueness is fundamentally tied to idempotency. You can't have one without the other. You have to think really deeply about what that means. To give an example, if we imagine a system that's doing financial transfers, and Jill wants to give, they want to get in, this is a hot topic. Jill wants to give $10 to Jack, right? So that background job is there. And it has some sort of transient error, so it retries. It is essential that our system, the idempotency guards that we place on that second execution, are not placed on a completely independent transfer of $10 from Jill to Jack. Right? We don't want, if these two things get overridden, if our sense of what makes a unique execution is not correctly applied, right? If we just said, oh, what makes a unique thing? This sender sends this amount of money to this person. The first time Jill sends Jack $10 and we're like, we've successfully done that. She tries to do it to him again. We say, oh, we're just going to skip that. This is an unsafe retry. Oops, that's a failure. You have to really understand what defines a unique execution of a thing such that you can differentiate new executions from retries of old executions. And that's why it is a required keyword argument. Of course, you can just default to the job ID, but if you have the time, you really should define an actual uniqueness set, right? Like whatever that might be, these arguments or the whole set of arguments, or you pass in other things, it's going to be foundational to really thinking through your system and its resiliency. The step method takes one optional keyword. You can say, run this in a transaction, yes or no. By default, it's a no. The interface, if you imagine like a step like this that does two database operations, right? You just want to put that in one transaction. That's going to make it idempotent, free, and cheap. Retries. We don't want that. The other thing it gives you is this context bag. You're going to need to stash values. You know, you do some computation in one step. You're going to need that result in some other step. Stash them durably so that you can fetch them later regardless of retries. Then it gives you a few directives to control behavior. You can tell the execution engine repeat a step, you can tell it to halt a step, and you can ask a question, is this step currently retrying? We're going to see in just a bit how that can be useful. But that's it. Like, this is the entire public interface of a CITIC job. It fits on one slide with properly sized font. I'm very proud of that. But 7 minutes left, let's hit the good stuff. How do you use these tools to actually build resilient jobs? What are the golden rules you need to follow? There are 4 of them. Let's walk through them with some examples. Firstly, focus on side effects. If you have work that is like preparatory work, this is very common, I find, in jobs that I write, you don't need to put that in a step. It's not doing anything. This has no side effects, right? You're inside of a perform method. Just do it before you start the execution engine. It's worth reminding ourselves that even though the interface that ActiveJob provides us for performing jobs are class methods, the performance actually happens at the level of an instance. You have an actual job instance. You can just use instance variables. That state is available to any of these methods that are going to be called by that engine. So do your preparatory work, do any just like read-only work up before you start the execution engine. Your steps are going to be defined by side effects. Speaking of side effects, it's really important that we isolate the different kinds of I/O in our steps. You do not want to have a step that does 2 different kinds of I/O. If you can do anything to avoid it, it's going to be very difficult to make that job resilient. If you carve your workflow up and each step is only talking to one particular I/O backend, it's a lot easier to make each step idempotent. And if every step is idempotent, then compositionally the entire job is idempotent. But the fact of the matter is that sometimes you can't avoid doing 2 different kinds of I/O in one step. A really common example is you make an API request, you create something, and you need that response because you're going to work with it in a later step. Right? I'm talking to an API over HTTP, and I have to store this in my database in this context bag. There's no 2 ways around that. How do you make this idempotent? Well, the first thing is you want to make each operation idempotent. The context bag is already idempotent. It's built to be idempotent. It's functionally a put. You can call it 5 times. It doesn't matter. Everything will stay the same. How do we make API posts idempotent? This is probably the most common example. Well, you should always check, does the API that you're talking to support idempotency keys? That is a great innovation. Stripe really led the way on that. You should be using them. Always go and check. Unfortunately, most APIs don't. That sucks. And we just have to deal with this fact, right? If you want to make an API post idempotent, the only way to guarantee it is to check before you write, right? If you build this and you run a simulation, you are going to find there are multiple error locations where you will get 2 resources created in that API. There's no ways around it. And I know it's a little bit frustrating to be like, well, now I have to do 2 API requests every single time just to ensure that this is safe. Like, I just hate that overhead, especially because definitionally I know on the first pass, it's fine. That's where the step retry comes in. If you really wanted to make this as optimally performant as possible, You'd say, only try to check if I've already created it, if I'm retrying. If it's the first pass, just go straight to post. I'm pretty confident that I haven't done this already. If I'm retrying, let me see, where in this step did it fail? Did I already create it or did I not? And this is as good as it's going to get. Sometimes you're going to have to do 2 API requests to make sure you don't create 2 resources. But by ensuring that your step methods are idempotent, like the composition just follows. Your job will be idempotent if you're using a workflow engine and it's performing correctly, which it does, like that is a natural guarantee. But if you are using a workflow engine, one thing that is true, and it's worth flagging, is that you can't mutate the workflow definition. You don't want to see this in a pull request. Because if you deploy this, and there are any jobs in the queue, they're mismatched. Now, the engine is going to just throw up its hands and create a permanent error and say, hey, you mismatched the definition that I just got from this job and the definition that was put in the database. I don't know how to resolve it, so you screwed up, and this will go to the dead set. See you in a bit. If you want to do this safely, what you need to do, and this is very similar to strong migrations, right? Like we are embracing resiliency, we're embracing safety, and that means that oftentimes we have to do a little bit of extra work. You're going to have to clone that job into a new class. You're going to have to give it a new name. You're going to have to tell your application only enqueue the new job with the new definition. You're going to have to deploy that change. You're going to have to wait for that deployment to get there. Then you're going to have to look at your job queue, and you're going to have to wait until the old job is completely drained. And then you should wait double that amount of time to make sure you actually had every single place where you were enqueuing it and you don't get new ones. And only after you're 100% certain that there are no new instances of that old job in your queue, then you can delete it. Now, if you want to rename the new job back to the old job, you're going to have to do this 1.5 times more. That kind of sucks. It is worth saying, though, as I said, the engine will throw up a permanent failure. So if you're okay with manually resolving all the jobs that get sent to the dead set, feel free to just send that up. But just know that that's what you are saying. It's like however many jobs there are that are currently running for the old definition, when I make this deployment, you are going to have to manually figure out how to get them to some completed state in the console. But those are the golden rules for making your job resilient. There's so much more I wish I could say. I would love to have had like an hour, maybe 2, possibly 5. I'm just going to flash some stuff. And if you're interested in these things, like come and talk to me afterwards, or we can hack on this stuff in the hack day. There are some higher order patterns. One of the things I get a lot is like, workflows, they're only linear sequence of jobs. Like what I really want is like a fancy DAG, and I want like all of this fancy. You don't want fancy, you want reliable, but it's worth remembering that you can build fancy on top of reliable. We've already looked at how to do external I/O, right? Like we want to check the step retrying, always do a get before a post. We've already looked at how to do internal I/O, right? Make sure those are in transactions. You can do fancier stuff though. You can have iteration. For those of you who've ever used the Shopify job iteration gem, we have a lower level primitive. You can do it yourself. I wish I could spend more time on it. That's resilient. You have to do a lot of stuff to make it resilient, but there you go. You want to do delays. You want to do some work, then you want to wait 3 weeks, then you want to pick back up and do more work. You do that resiliently. You can do that. There you go. There's a pattern. I'll leave it on there for 5 seconds. You want to do job batching. I'm not trying to like take money directly out of Mike's pocket, but you could do Sidekick Pro style batching if you control everything yourself. It's more code than fits on one slide, so you have to come and ask me about it later. In general, though, these are the principles that you're going to need, and these are the ways in which I think Acidic Job provides you a minimal set of very sharp knives to allow you to define your jobs in such a way that they will run reliably and resiliently over time. Chaotic Job, of course, paired, always have good tests, and that's fundamentally all you need to scale a resilient job layer. Thank you.